Welcome to Study Time, a televised home learning program produced by Rwanda Basic.
Hello, Senior 6 Chemistry students. How are you? Welcome back. We are still on our Unit 15, which is about radioactivity. Alan is my name, still with you. And now we are heading into Lesson 4, which is about radioactive decay and half-life. I hope we are fine and still moving on. To take a quick recap on what we looked at in the previous lesson, we looked at integrated decay equation, NT equaling to N naught exponent negative lambda T. And we derived it and did a few examples, but in general, what does it imply? Remember, radioactive decay is a random first order reaction, meaning for it will keep taking place provided you still have the unstable atoms. And that is what that equation implies, the exponential decrease as time passes. And using that illustration, as you can see on the slide, if you have, for instance, strontium, and you start with 100 grams at time 0 years, it will keep on decreasing as time goes on until the strontium atoms, or the nucleus of the strontium atoms, gain stability. And when they are completely stable, then the decay will cease to occur. But provided they are still having instability issues, then they will keep on disintegrating. And of course, we looked at those conditions that bring about instability in the nucleus. So basically, that is what we looked at. Then I left you with the exercise, that number which I left you to go and try. I hope you tried, and if you did not try, please endeavor to always try the exercises. They are there to help you conceptualize the content or test your comprehension. So to those who tried, we are going to go through it together so as you can correct your answers or you compare your responses with what we shall agree on. Now let's turn on and go through that exercise as correction. Exercise 3, corrections. We are doing the correction. So, what was the question saying, or what do we have from that question? As usual, you need to outline the data you have so as you can use it. The disintegration rate constant that gives us lambda is given to us as 2.85 exponent negative 3 per second. So that is converting sodium to magnesium. We are to calculate the fraction. So we have time, which is 150 seconds. Do we have NT? Remember our equation? The equation we are going to use, NT is equal to N naught exponent negative lambda T. Remember that. So what do we have? We have lambda, we have time, we NT and N naught. These we don't have, but according to the question, it is asking us to determine the fraction, indicating these will combine to form NT over N naught. This is the fraction that we are being asked. This is the fraction we are to determine, indicating we don't necessarily need their values. For the sake of understanding, look at that. They're saying the conversion of radioactive sodium into magnesium. Well, we do not know the specific isotope of sodium, But from the understanding of that, if we use 2311 sodium as the unstable, then it is decaying to give magnesium, which in this case would be 23, then 12, since they specified to be magnesium. And as we can balance this, you'll find it will be the alpha, or no, it will be the beta decay. Remember, for beta decay, the number of proton increases. So possibly this is what happened. Again, the data does not specifically say this, but I'm bringing in the aspect of transforming sodium to magnesium. By the mere fact that we have the proton numbers 12, that gives us to be magnesium. So this indicates that this is possibly the isotope of magnesium. Let's now go to our calculation. How do we get NT? Remember, we said we're using our equation. So in this case, I'm going to rearrange NT, N naught. If I bring this back, it will be NT over N naught directly, which is exponent negative lambda T. So can we substitute? Yes. The NT over N naught, the fraction that we want, will be exponent. Just substitute the values. Negative 2.85 exponent negative 3 times 150. Just combine, and using our calculator. Of course, you know we are doing the calculations at this moment basing on our previous lessons. I expect you to come with your scientific calculator. Now, how do we directly substitute this? You just go to your scientific calculator. If it is FX 82 or 100, it will still give you the value. Press Shift. Then, like as I explained last time, there is the third button. It indicates lean. Shift, then lean. It will directly give you this exponent. Then you substitute the values the way they are. Let's quickly do that. Negative 2.85. Yeah, it's giving us 0.65. So we can convert this to a percentage, and we get 65% as the fraction. But still, you can leave it as 0.65, which conforms it to be a fraction. So that is the fraction that would remain after 150 seconds, and you're done with that calculation. Basically, that is what you go through. Now, let's quickly look at today's lesson content. Allow me to introduce it unto you. We are still on lesson 4, and it says radioactive decay and half-life. That is our focus. So, in this content, we're going to be looking at defining what is half-life and how exactly does it relate to the stability of atoms. Then we perform calculations involving the half-life. Our objectives, and of course the key aspect you should not miss in this lesson, is the definition of half-life and how to use half-life to perform calculations. So we have two objectives we are to work on. One is we are to relate the half-lives of atoms and their stability. Is there any way one can look at the half-life of a certain atom and tell whether it is stable or it is unstable? So that is one of the objectives. If you can look at the half-life and predictively tell that this will be stable than the other, then you will have really conceptualized the lesson work. Then we to use the formula for the half-life and perform calculations. As expected, you should perform the calculation accurately, not simply performing, but do it accurately in the expected way. So that is what we shall focus on today. Half-life. Half. Basically, by the mere understanding or the mere hearing of the word half from your elementary mathematics, that tells you part of something. It is half, we're talking of half-life for radioactive atoms. So by definition, it is the time taken for the concentration of reactants, in this case, the amount of radioactive atoms. It is the time taken for the amount of radioactive atoms to disintegrate into a half the original. What do I mean? Let's internalize our graph. Suppose I start with one atom. The time that it will take for that one atom to decay or to disintegrate and give a half of it is what we call the half-life. Similarly, the half of that atom disintegrating, giving a quarter, is still the half-life. So, in brief, any original value you're having at the start, disintegrating or decaying to attain half that value, the time it takes is what we consider as half-life. So we understand in this case, if you have 100 atoms reducing to 50, then the time it has taken for the 100 to reduce to 50 is what we call the half-life. As I had said, what exactly does the half-life tell us about the stability of the nucleus or the stability of the atoms? As you would imagine, the more the time it takes for like 100 atoms to disintegrate to 50 atoms, if they take longer time, that indicates they are stable. If they take short time, that indicates they are relatively unstable. So that is exactly about the half-life. Let's use a few examples. Look at uranium. We've always heard of uranium, we've always heard of nuclear power plants and so on. So let's look at uranium. We compare it with iodine and bismuth. What do you notice? I would ask you a question. Which of those three atoms, which one of them is more stable than the other? A range from bismuth to uranium, which one is more stable? Looking at their half-lives. Yes? Quick math. So uranium, for instance, uranium-92 with the atomic mass of 238 takes about 4.5 billion years to decompose. You can see, to attain billion years, imagine, and even go to 4.5. So indicating for it is actually stable, it does not easily decompose. Look at iodine. It simply requires 8 days to disintegrate to half the original value. And bismuth, just 19. A few minutes, it will have disintegrated to a half the original you are having. So from this, you can notice that the more the time for an atom to disintegrate, then the more stable it is, or the more its nucleus that is very stable. So looking at that, we can compare the decay constant and the half-life. Let's quickly compare the decay constant and the half-life. Those two are related by that expression. Again, the question is, where does it come from? Where is that relationship coming from? We can quickly derive it. This is the relationship between lambda, which is the decay constant, and half-life. So we are now going to relate half-life and the decay constant. So remember our equation. We're actually going to use it from the decay equation, which is nt equaling to n naught exponent negative lambda t. Again, this n is still, you can use A, you can use M, but you have to define what they are. For our case, we had already defined what is nt and what is n naught. But if you're using a different symbol, then define it at the start. So we're having this. So let's rearrange. You will find you're having nt over n naught equaling to exponent negative lambda t. Let's introduce back our ln. If we introduce the ln in our equation, you'll have this directly would be ln nt over n naught equaling to negative lambda t. By applying the ln, the exponent will go. Then this comes over here. Can we quickly indicate in the, or bring in the half-life? So at our time, that is now the assumption we're taking, at our time equaling to t1/2. In other words, remember to get this, we consider the time to be at 0 when the disintegration has started. So if we take time to be at t1/2, when half of the original has been attained after disintegration, then what will be nt? Nt will be a half of n naught by definition of half-life. Now we can simply substitute this in our expression here. Ln, where we have nt, we simply substitute it with a half n naught. Where we have n naught, it stays, equaling to negative lambda. Where we have t, we substitute it with t1/2. T1/2 implying the half-life. So by your math, these two will go. What do we finally have? Ln ½ is equal to negative lambda t1/2. Using your math, 1/2, we can write it as 2 inverse. Indicate here we shall have 2 ln inverse. Using your principles of math, a half is similarly written as 2 power negative 1, or 2 inverse, equaling to negative lambda t1/2. So we bring this here, negative ln 2, negative lambda t1/2. What do we notice? The negatives will cancel. We end up having t1/2 equaling to ln 2 over lambda. If we can substitute the value of ln 2, you end up having t1/2 ln 2 lambda equaling to, substitute ln 2, 0.693 over lambda. So basically, either of these, you can maintain ln 2, or you can substitute the value for ln 2. Now, this is the relationship between half-life and the decay constant. What do we notice? How can we bring this to words, this mathematical expression to words? Can we bring that mathematical expression to words? you notice in our expression for decay constant and half-life, we do not have concentration involved in, or we do not have the amount of atoms either at the start or after some time involved in our expression. So what does that tell us? That is the implication of that relationship. It implies the half-life for this radioactive decay is independent of the amount of atoms you're having at the start, or the amount of atoms you're having that are undergoing decay. So if you're having, for instance, let's use iodine as we are having it on our illustration. If you're having 20 atoms of iodine 131, which is radioactive, its half-life is actually 8 days, as we noticed. So if you're having 20 atoms, after 8 days, those 20 atoms will have decayed up to 10, or the 20 will have reduced up to 10 atoms after 8 days. Similarly, after other more 8 days, the remaining 10 atoms will have reduced to 5. And even after other 8 days, the remaining 5 will have reduced to 2.5, and so on and so forth and so on. So the amount remains the same irrespective of the amount you're having at the start. That is what we imply. The time required for the number of atoms to disintegrate will be the same if at all you have 1 or you have 0.5 or you have 0.7. To reduce to a half, it will always remain the same. That is the implication of the half-life in regard to decay constant. So that is what we can quickly look at. Let's now see a calculation relating this half-life and the decay constant and how we can quickly come up with the answers. That is the practice question. Let's go to the practice question. As it is indicated on the slide, we can interpret it together. We have a sample of fresh wood, which gave 20 counts per gram per second. This is fresh wood, indicating that is the start. It is giving us 20 counts per gram per second. So after it has been detected using radioactive carbon-14. Remember in the assignments I gave you, the start was to read more on how carbon-14 is used in carbon dating. This example is about carbon dating specifically. So what does the question say? After having the fresh wood and they determined the counts, they looked for a similar wood from one of the prehistoric sites in East Africa, and it gave 5 counts per gram, indicating at that moment, the one which has given us 5, it has already decayed. So it is giving 5 counts per gram per second. The question is, determine the age of the wood if we're having half-life as 5. So we're having this information. The question is we are to determine the age for the wood. In other words, the time that is required for this fresh wood to decompose or to decay up to 5 counts per gram per second. So let's use this information in our equation. We have T a half indicating we can get the decay constant. So in this case, the decay constant will be, quickly substitute, it will be 0.693 over half-life, which is directly over 560 years. We maintain the years, And so the decay constant will be considered in terms of per year. It's giving me 1.237 exponent negative 4 per year. That is our decay constant. So we are to determine the time or the age of the wood. In this case, we still use we can use this. We can use this from ln nt over n naught according to negative lambda t. Our emphasis is on getting t. We have the rest. Can we simply substitute? So ln nt, which is 5 over 20, equaling to negative 1.237 exponent negative 4 times time. So what will be time directly? If we can simply substitute. Okay, ln is 5 divided by 20. So exponent negative 4. So I'm getting time as 11206 years. So in this case, we can simply conclude and say the age is 11206 years. So this is the age of that wood, basically, and you are done. So the principle in here is we are applying the carbon dating, one of the uses of radioactive atoms, and seeing how we can determine the age of a certain component that decayed long time ago. So that is it for today. Thanks for being part of the lesson. And as usual, I always leave you with an exercise. This is exercise 4. Please stay safe. Attempt as many exercises as possible for you to conceptualize the content. Bye.